Yeah, thanks for having me here. Thanks for being here also. Today I'm going to talk about microarchitectural attacks in general and in specific Meltdown and Spectre. Just before we dive into the topic, I want to start with some vulnerability assessment. So Meltdown and Spectre are CPU vulnerabilities. They exist in hardware, basically, and they were discovered in 2017 by 4 independent teams. And during the responsible disclosure, Intel got us connected, and that's how things evolved. And there will be 2 papers with also authors from all 4 teams soon enough. You already saw the draft versions of them, I guess. Yeah, due to an embargo, we only released them in early 2018. And yeah, there was a lot of news coverage. You might have seen it, Fox News, CNN. We had BBC, CNBC. There's a Wikipedia page. I really like that. Also for Spectre, another one. We also liked the XKCD comic and the one on Comet strip. And then we had this tweet from Edward Snowden. And this was funny because Michael Schwarz, who posted this on Twitter, this video, later on got the question from other people, and they asked him how he dares to just copy this video from Edward Snowden without giving credit to him. So, yeah. They didn't see that the time stamp was earlier than the timestamp from Edward Snowden. So let's first talk about Meltdown. So what is the underlying issue here? For that, we have to understand how hardware isolation works. So we have, if we look at a modern operating system, at a modern system, you have the kernel isolated from the user space. So you have some huge wall between the user space and the kernel space. And yeah, you can't cross this wall except for with syscall. And this is a well-defined interface, so you can't cross it if the kernel doesn't want you to cross it. So what happens here is also that the user space applications can't have direct access on each other. So for instance, my photo app may not have access to my private emails, which is a good thing. Or the calendar app might not have access to the private emails. Probably a good thing. What Meltdown does now is it breaks the wall. So the wall is gone, and the user applications can access anything in the kernel. They can access the entire physical memory, and that includes all the memory of the other applications as well. Great. So here, I have put that on the slides explicitly. Meltdown can read the entire DRAM. There's no region in DRAM that Meltdown can't read. Okay, next point. What are the requirements for Meltdown? You need an Intel CPU or an ARM CPU. There's one ARM CPU that is affected by this issue. And AMDs and other ARMs seem to be unaffected, but we don't know for sure. So far, no one was able to reproduce it. And the problem here is that the permission check seems to be done in parallel to the load instruction. So it's a race condition between the permission check and other dependent operations after the permission check should have happened. There are different variants of Meltdown, specifically 2. And the second variant of Meltdown just reads privileged registers. And here, yeah, this is typically, if we think about this method, we think about ARM CPUs. There are also Intel processors where this has been reported, but this affects mostly ARM CPUs. And there you can read the content from privileged registers. What do you need to do to exploit this? Well, you need some form of code execution on the device. So for instance, an app. It might be possible to exploit it from JavaScript. I can very well imagine that. And then you can, yeah, basically read the entire memory. Untrusted code can read the entire memory. And fortunately, it can't be triggered remotely. Probably, I guess. But there's proof of concept code online to exploit it from native code. So yeah, I would expect that everyone now is aware how you can exploit it. And so we all need to install our patches so that we're protected against it. And let's hope that the software and hardware vendors now get the patches right. So Meltdown is really easy to reproduce. If you hand the proof of concept that we have put online to some undergraduate computer science student, they will have a working attack which can read arbitrary memory within an hour on their machine running. So this is really easy to reproduce. So this is a huge threat, therefore. Spectre is a bit different. In Spectre, you actually don't try to cross some wall, but you do something different. You try to trick someone into spilling their secrets. And you do that by mistraining branch prediction. And branch prediction is used all over the code execution in your processor, so it is used all the time. And when a different process tries to predict the branch, it will predict the branch based on the virtual address, because it has to be really fast, so it will use the virtual address. And this process, you can manipulate that and have the processor mis-speculate. So it will speculatively execute code which should not be executed, in some cases even code which would never be executed in this program. Yes, this is the case of indirect calls, for instance. So Spectre convinces the other program to execute some code, and by that spill the secrets. It affects Intel CPUs, AMD CPUs, also some ARM CPUs are affected, a wider range of ARM CPUs are affected, and the problem here is speculative execution of branches, and there you do memory accesses in there, or other things that leave microarchitectural traces. Memory accesses and cache hits and cache misses are by far not the only microarchitectural effect that we can observe. What about the exploitability? So again, Spectre requires, just like Meltdown, code execution on the device. So untrusted code can convince a trusted region to spill their secrets. For instance, in JavaScript, you could break out of the sandbox. And yeah, it can be triggered remotely to some extent, yeah, through the browser, but it's still some form of local code execution. There's also proof of concept code available online, and you need a lot of information about the environment. So you need to know how to mistrain the branch predictor. So it's a bit more difficult to reproduce. Maybe hard is a bit too strict. I think it's still very much doable within a day's work. Okay, let's go for some background. What are we talking about here? We are talking about microarchitectural attacks. It's related to side channel attacks. And side channel attacks, probably you all know that from the movies. When you want to crack a safe open, how do you do that? You use a stethoscope and you listen to the clicking noises that the safe lock does while turning the wheel. And when one of the latches snaps in, it will make a clicking noise, and you can hear that, and then you know you have to turn the wheel the other direction. So with that, you will figure out the secret combination of the safe. Of course, in modern processors, we don't have clicking noises most of the time, but we have other effects, and there we get to the CPU cache. Let's think about this very simple program where we access a local variable or a global variable twice. The first time we access it, it will be a cache miss. Then, if it's a cache miss, the processor has to fetch it from the main memory, from DRAM. So it sends a request to DRAM, and then it gets a response later on, a few hundred cycles later, and then it's loaded into the cache. The second time we access it, the processor has it cached, so it's a cache hit. So the first one was a DRAM access, it's slow. Second was no DRAM access, so it's fast. If we have a timing difference between something fast and something slow, or more in general, if we have some difference that we can measure, it could also be some behavioral difference, then we have something where we might build an attack. Flush and reload. We start with this flush and reload attack, which is a very easy to understand cache attack, which was discovered in 2014 or end of 2013. And here we assume that the attacker and the victim have some shared memory, for instance, a shared library or some binary. All binaries are shared among all processes if they open them with mmap. And if some memory location is cached for one of the processes, it's cached for both. Now the attacker has the x86 CL flush instruction at disposal. So it can just use this flush instruction, throw something out of the cache, and then at some point later on reload the data into the cache and measure how long it takes. And if the victim in the meantime accesses the memory location, then it will be cached. And if the attacker now accesses the same shared memory location, it's fast. Otherwise, if the victim didn't access it, it's slow. Let's look at a histogram so that you see that this is really a clear timing difference. This is the case if the variable is cached, or if we try to have the variable cached. There might still be cases where it takes more time, but most of the cases here are around 50 cycles. And if I'm trying to throw the data out of the cache and then access it, I have timings that are above 200 cycles. And there is not a single instance where I measured a timing below 200 cycles, which is quite nice because then you don't have to know anything about statistics. You can just put a threshold there and be done with the distinguishing the two cases. We will build a first attack with that. Here I just iterate over libgedit and type keys into gedit while doing that. And I print the number of cache hits that I observe on these addresses. And then I will just pick one of those addresses that had like maybe something around 20 cache hits would be a good thing because I didn't press that many keys, so if it's too much, it's bad. But maybe this address here, 24, sounds good. Let's just copy it and see what happens if we now print a message every time we press a key. This is great. Every keystroke. So we have some timing measurement here that's accurate to something like 300 nanoseconds. And we can observe every keystroke on a time scale that is done in this editor now. We can do that on a different shared library. I also did that on libgdk, which is part of the GTK library. And I got this as a result. They do some binary search to translate key codes. And binary searches are great because there you have these leaf nodes, which are only accessed if it's exactly that key. For instance, here we have the key n, which is only accessed, this address is only accessed if I press key n, which is great if I want to figure out a password or something, right? Or I don't know what else you could do with that. But let's get back to out-of-order execution after this, cache attack primer. Out-of-order execution reminds me a lot of cooking because while cooking, I always run into the same problem. The last step of the recipe, and I'm really bad at cooking, but the last step in the recipe is always something like serve with cooked and peeled potatoes. And I'm like, okay, there are the potatoes. They are not cooked, they are not peeled. So now I have to wait for an hour. Probably the guests are already arriving in the meantime, which is quite embarrassing. It's latency. We want to avoid that. And the same problem exists in modern computers. And they also want to avoid that. So let's look at the recipe here. Maybe I could parallelize some of the things here. And the things that I have to do afterwards that depend on previous steps, I have to do them afterwards. And the same thing happens in the processor. So here also, the things that can be parallelized, the processor will parallelize them. And we are speaking of out-of-order execution windows of something like 200 simple instructions that a modern processor runs out of order, that it runs ahead of the instruction pointer and already executes those instructions out of order. So with that knowledge, we are ready for the details. Let's just try to access the kernel right away, right? This is the kernel address. Some interesting information will be written there, and we'll just read it and print it, and that's it. Oh, that doesn't work. Okay, that's not surprising. That's what should happen, right? Kernel address, you can't access kernel addresses. But what happens if the executions are run out of order? Are the privilege checks done in time? Well, maybe we try some other experiment first, some really minimal experiment. We access the null pointer. Null pointer, clearly this would trigger a segfault. And then we access some offset in some array. Should be unreachable, right? So this should never be cached. If we compile that, compiler is not happy. Static code analyzer is also not happy. Shouldn't do that. And if we run the code, what happens? The unreachable code line was executed. Oh, that's bad. And the exception was still thrown, but only after the memory access was already performed. This is quite bad, because then we might build an attack. Okay, out-of-order execution leaves microarchitectural traces. We learned that. For instance, the cache. And we give them a name. Transient instructions is a good name, we thought. And we can observe the execution of transient instructions indirectly. So we combine the two things that we had just had. The first thing, the access to the kernel address that triggers a segmentation fault, but also reads the data into a register. And the second line, now we have the register value here as a index to the array. And then we check which part of the array is cached. And the same thing as before works, and we see what the secret value was. That is Meltdown. It's really simple to understand and really simple to implement. So it's a bad thing because it's really easy also for attackers to reproduce that. Yeah, the permission check is not fast enough in some cases. Yeah, and we can read arbitrary data from the kernel with that. Too slow. Yes, we can leak the entire kernel memory, and in the kernel memory, there's usually a mapping of most of the physical memory. On Linux or OS X, it's even the entire physical memory that is accessible through the kernel space. And what you can do then is, you just write a small program and you pass a physical address to this program, and this is the physical address of the password buffer here. And you can live read this string that the user types in, because you read until the value there is not 0. So you always read the last character of the string. And another nice example that we tried was
Yes, the reflection in her eye.
Let's run this through video enhancement.
Edgar, can you enhance this?
Hang on. Can you enhance the image from here?
Can you enhance him right here?
Can you enhance it?
Can you enhance it?
Can we enhance this?
Can you enhance it?
Hold on a second, I'll enhance it.
well, depending on the image format, we actually can. So here you can see this is a Meltdown attack on an FLIF image, and then the image gets slowly better and better. Okay, that's it for Meltdown. Let's start with Spectre. With Spectre, we are thinking about speculative execution, so it has to do something with conditional branches. So it's either true or false, and one way is right and one way is wrong. And so there are different options what could happen. For instance, in case of a bounce check. Let's assume the bounce check returns true. Then there are two possibilities. Well, the prediction could also be that the bounce check will be positive. Well, that's good. Then we're fast, right? That's the case that we want to have. Not so good if the condition is true, but the processor speculates it's false, then yeah, it's slow. Yeah. Also nice if the condition is false and the processor also speculates it's false, then again we're fast. And if the processor speculates it's true, then yeah, then it's insecure, but also slow. Okay, that's basically the idea behind Spectre. So you have this one case where you can leak secret information. How does it work? We look at a very simple example now. We have an index here and some string. Part of the string may be read by the user space program or by the other program that interfaces this code. And you have a bounce check here that guarantees that you can't read any of the secret data. And then you have some lookup here, some array lookup. We looked at binaries, and this is a quite common pattern that you have some array lookup with some secret value. And you can also, if you don't have that with Spectre variant 2, you can even combine that with different gadgets. But what you would do here is you start with index 0 and slowly iterate over this buffer, passing valid values first. So values that are inbound. And here you can see it first might speculate wrong, but then it will execute the right direction. And as you pass the next index, it will already speculate the right way because the prediction now leans more towards the then branch. And then it will be fast all the time. And as we get to index 4, the prediction will still go to the left side, but the execution should go the other side. And there we did already do the memory access, and this already leaked the secret key byte. And the same goes for offset 5 and 6. Yeah. There's a similar case with Spectre variant 2. I thought of a very minimal example here, and I came up with this. We have some animal class, which is an abstract base class, and then we have some derived classes, fish and a bird, and we can pass to a method that calls the move method of either of those objects. We can pass one of these specialized objects to this method. And the method will, the fly method will do some memory lookup that we don't want to do for a fish. And for a fish, we want to run the swim method where it doesn't do any weird memory accesses. And this index here now might be some member variable of the fish of the fish object, or it might be some other variable that is referenced in at the right memory offset. You must see that here this is very similar to a type confusion attack. Basically, you're calling the wrong method on some base object. So you could do anything as in type confusion attacks here. What will happen if the processor starts speculating here? It might first speculate the wrong way, very plausible on the first run. So it might speculate the wrong way, and then it will see, okay, I should execute the other one, and it will directly adapt to that, and now say, okay, next time I'm here, I will predict the fly method. And then we pass the bird again, and it's fast, that's great. And if we pass the fish there, then it will still run the fly method for the fish. So that's Spectre variant 2. The most simple example that I could think of, nothing with mistraining branches in either of those cases where you mistrain across processes. This is only within the same process, which is much easier because then you don't have to do any fancy things, or you also don't have to know that much about the processor if you stay in place. Okay, yeah, and then it will, of course, adapt the prediction again. So the question is, what can we do against Meltdown and Spectre? And there were a lot of patches against Meltdown and Spectre. So one idea that we already had in 2016, before we were aware of the Meltdown attack, but to cope with several other attacks, was the Kaiser patch set. And there we thought, okay, kernel addresses in user space are a problem. So why don't we just take the kernel addresses and remove them if not needed? We don't need them most of the time. So maybe the user space accessible bit that is implemented in page tables, the check for that bit might not be reliable. So maybe we should just unmap the kernel space. And yeah, that's what we proposed as the Kaiser patch said. And then kernel addresses are no longer present, or at least only a few kernel addresses, as few as possible. And the nice thing is, since the processor can't know to which address, to which physical address, a virtual address will resolve, it could resolve to any physical address, it can't do any prediction because memory which is not mapped cannot be accessed at all. So there can't be any misprediction there. Yeah, we called this Kaiser, and it stands for some longer sentence. But also, I think the connection to Linux is also nice because it's the largest penguin, emperor penguin, Kaiser penguin on German. Yeah, what does it do? Well, we have this wall here in modern operating systems between the user space and the kernel space. And what we do is we basically say, okay, it's fine if a user space application runs through this wall, it's fine, but we just must take care that there's nothing behind this wall, right? So this is what we do. So when we are in kernel space, the kernel can't directly access the user space nowadays because of SMAP and SMEP memory protections. But when we're in user space, the user space applications could run Meltdown on this hardware, still possible, but there would not be anything there. Problem solved. So we published the Kaiser patch set in July 2017, and Intel and others have put a tremendous amount of effort into that and built a patch set that is actually working, not just like the proof of concept thing that we had in the beginning. And they renamed it into KPTI because they didn't like the name Kaiser for some reason. Microsoft also implemented a similar concept in Windows 10, and Apple already had something like this before, and they revived it, and it's called Double Map there. And during the responsible disclosure, at some points we asked ourselves, oh God, the poor developers, we ruined their Christmas. We're very sorry for that. But it was great work by all the developers involved there, thousands of people. And I'm really happy that now an idea that I proposed is integrated into every operating system. That's kind of awesome. Wait a moment. Duplicating everything. So basically you need two page maps level 4. So all the memory hierarchy there is duplicated. Isn't that slow? Yeah, it depends. So if you run it on old hardware, we only suggested that you would do that on Skylake or newer processors in the paper that we wrote. There, the performance stays in limits that are okay. On older hardware, it can be horrible. The worst that we saw was one benchmark that an Amazon engineer posted with like 400% overhead. And we were like, okay, this is definitely not for something like reviving KSLR, if it's 400% overhead. Yeah, modern CPUs have additional features that make this thing faster, and then the performance overhead may be as low as 2%. Or we saw the Phoronix benchmarks, and they reported that while computer gaming, your computer might even run faster than before, because now they also use PCIDs, which have some performance advantage. Okay, so this is it about Meltdown. Meltdown is not a problem anymore. So it is a huge problem. It was a huge problem, but now that we have patches against it, it's done. We don't need to think about it anymore. Maybe we should still keep it in mind because something like that might pop up again. There is this line in the Linux kernel where an AMD engineer said, okay, if it's an AMD CPU, then everything's fine. So maybe at some point AMD will start optimizing this part of their CPU, and they might run into the same bug, and then no one remembers it, and we will have a lot of fun again. But maybe let's think about Spectre. In Spectre, we could, of course, also speculatively access the kernel, but then again, we would exploit the same effect as in Meltdown. So what we do in Spectre is we let aside this Meltdown bug, but we now focus on just the speculative execution on valid memory addresses. So we do not directly access the kernel, but only convince other programs to reveal their secrets. And this is much harder to fix. And there's ongoing effort to patch this via microcode, via compiler updates, to recompile all the software. Yeah, a lot of work, and I think that will keep us busy for at least 1 or 2 more years until we have really got to a decent situation here where we can all relax again. A trivial idea that we heard a lot was, why don't we just disable speculative execution? If there is no speculation, then there is also no wrong speculation, right? The problem is that this makes the system too slow. The performance of modern processors depends crucially on speculative and out-of-order execution. You can't just disable it. There's no way to disable it in a generic way without redesigning the CPU. It's deeply integrated into the CPU and how the CPU works. So we need to find some other mitigations that can cope with speculative execution, but still try to prevent the cases where speculative execution leaks something. And yeah, so Mitigations. Of course, we could insert instructions that stop speculation. For instance, LFENCE or on ARM CSDB. And you can insert that after every bounce check. That will still have a massive performance hit, but maybe not as bad as disabling speculative execution completely. Yeah, so you can do that on Intel CPUs and on ARM CPUs. AMD also said they will also go with the LFENCE solution. Yeah, so for the speculation barriers, the LFENCEs, you need compiler support because you don't want to do that by hand after every bounce check. And this is already implemented in GCC, LLVM, and the Microsoft compiler. Yeah, it can be automated, but this is not really reliable. One of our colleagues, Paul Kocher, investigated that on a set of programs, and I think it was something like 6 out of 10 programs still had the Spectre vulnerability in them. So it doesn't work reliably, but we will get there over the next years. You can also explicitly say that you don't want to do that by using some built-in load no speculate. Okay. Let's look at this code here. Very simple code. It's just a bounce check and it says array n or fail. And if you would rewrite that to this new method, it would look like this. So much less readable, I would say, at least at the first look. And I'm not sure whether this is the right way to do that or whether the compiler shouldn't still try to automate that as Microsoft tried to do. Yeah, so the speculation barrier works if the code constructs are known, but there are loads of different ways to run into Spectre variant 1 vulnerabilities. In the end, the programmer has to take care about that, and we have to see whether automatic detection will be reliable at some point. And also, you will have a non-negligible overhead for these barriers. It will still be a performance hit of, if you would introduce that to every bounce check, still a performance overhead of something like factor 2, 3, or 4, something like that. For Spectre variant 2, I think the situation might be a bit better because Spectre variant 2 relies a lot on mistraining out of place, and you can prevent that. Intel released some microcode updates for that. The first, the IBRS, is some new mode, and when the processor enters this IBRS mode, it won't speculate based on anything before entering the IBRS mode. I'm not sure, so I read different documents from Intel. Some say it like this, others say it won't speculate based on anything outside of the IBRS mode. We will see whether Intel updates their different documents at some point to clarify this. Yeah, so the idea is lesser privileged code cannot influence the predictions here. Then we have the IBPB, which is basically a mechanism to flush the branch target buffer and then prevent that the processor will do a prediction based on previously learned things. Then we have the STIBP, which is basically a mechanism to isolate the branch prediction between the hyperthreads. So one hyperthread won't do a prediction based on what the other hyperthread has learned in the past few instructions. There's also a software mechanism against Spectre variant 2 that was proposed, RedPolines. And if we look at the code, I have some assembly code here. You would take every indirect call in your program, and you would start by replacing the indirect call by some instructions plus some indirect jump. The next thing you would do is you replace every indirect jump by this construct here. Every indirect jump. And this does some weird things that we usually only know from return-oriented programming. So it abuses the return instruction to jump to some function. And by doing that, we can trick the speculative execution, because the speculative execution will see, the speculative execution for now doesn't understand that this here changes the call target here of this return instruction. The return instruction is also an indirect call in some way, or an indirect jump in some way. But the processor doesn't understand that this modifies the call target here. Else they would speculate correctly at some point if they would learn that. So what the processor does is it sees, okay, you call here, you will immediately return, so I will speculate here. And it will run in this endless loop forever. Yeah, so it always predicts to enter an endless loop. That's interesting. So it prevents that you're predicting the wrong function, but it also prevents that you're predicting the correct function, right? So you're always losing performance. Also, on Broadwell or newer CPUs, the return instruction may fall back on the branch target buffer for prediction. And there are also mechanisms for the return instruction for predictions. Then there are microcode patches again to prevent that. And so situation is a bit complicated there, but I think that we can work towards getting that resolved. ARM also did some things with respect to variant 2. So they provided a hardened Linux kernel, and this one clears the branch predictor state on context switches. They don't have hyperthreading, so they don't have some of the vulnerabilities that Intel had. And they introduced new instructions for that. Or you could enable MMU also to do the same thing. And this has a non-negligible overhead again. But yeah, we don't want to have these vulnerabilities in our systems, so we at some point have to accept the overhead. For now, I hope that more modern CPUs will reduce the overheads again. Also, things that people proposed to us were preventing access to high-resolution timers. That doesn't work. As soon as you have multi-threading, you can build your own timer. And the funny thing is, we showed that in a recent paper, the most accurate timer that you can get on Intel CPUs is usually RDTSC. Reading the timestamp register, it will give you something like if you have a 4 gigahertz CPU, it might have something like a 0.25 nanosecond resolution. Although it will only usually do an increment every 3 cycles, so something like 0.75 nanoseconds. Turns out, if you build your own timer using a timing thread, you're a bit faster than the RDTSC instruction. So no disadvantage there. Other suggestions were to make the flush instruction privileged. You can also just do cache eviction. The cache has a limited size, and it is organized in a very specific way that allows you to access only a small number of addresses and evict the cache through that. And you might know that flushing things from the cache is also the tool that we need for row hammer attacks. But we showed in 2015 that you can also do that with cache eviction. So cache eviction is quite fast. It's fast enough to do row hammer. It's definitely fast enough for our attacks here. We can also just move secrets to the secure world, right? To SGX or something like that. Unfortunately, Spectre attacks work on secure enclaves. So maybe that also doesn't work. The question is, what did we learn from all this? I think we learned from this that we have ignored software side channels for many, many years. There have been the first reports that you could use the microarchitectural effects to mount timing attacks on cryptographic algorithms. And what the entire academic community said was, well, it's a problem of the algorithm, right? It should be implemented in a correct way that is not leaking secrets through timing differences, not doing any timing secret-dependent behavior, which results in different timing. And this was quite established, so this is still the case. So if you design a crypto algorithm, if it has a timing difference in one or the other case, people will immediately consider it insecure. And that's also the same thing to do because the processors are as they are, and we need to cope with that. But we saw different attacks. For instance, attacks on ASLR. We did one, the prefetch side channel attack. Actually, this was already highly related to Meltdown in the way that it works. And there we reported this issue to Intel, the prefetch side channel attack. We talked to Intel, and yeah, the response that we got from different, so basically everyone we spoke to, not only Intel, was basically, yeah, ASLR is broken anyway. Why should we care about this, right? But in the end, ASLR gives you some probabilistic security that's still valuable. And having a side channel which lets you defeat it in like a second is really a bad situation. Then we had these attacks on SGX and Trust Zone, and there we attacked an algorithm. Similar algorithms are used, for instance, in crypto wallets. In I think it was not a Bitcoin wallet, but some other coin, some wallet, and they suggested, yeah, we do all the operations in SGX because there it's secure, and we keep your private key in there, and there it's secure. And we showed that if an insecure algorithm is implemented inside SGX, we can leak the private key. Now, what Intel said was, yeah, the side channel attacks on SGX are not part of the threat model, right? Why should we care? And the interesting thing then is if the vendors just copy paste this statement and say, yeah, this is outside of our threat model. It doesn't work like that. If it's outside of their threat model, it might be exactly in my scope. So maybe I should care about if my customers lose money. Okay, so what we learn is we solely optimized for performance in the past years. And maybe that's something that we should change. Maybe performance is something that we want to achieve, but not at all cost. One thing that I also want to mention, when you read the manuals, the Intel manuals, after learning about a side channel, we also had the same thing when we found the prefetch side channel. Afterwards, you read the Intel documentation and you realize everything was documented. It was just written in an obscure way that you didn't understand the implications. And probably, so I don't know whether they understood the implications. They might not have understood the implications. But once you know it and you read the statements again, you see, okay, it should have been clear all along, right? It says explicitly, speculative execution may leave data in the cache. So yeah, it should have been quite obvious. What do we learn from it? Maybe in our industry and also in the scientific community, we must go through some evolution that other industries already had. For instance, the car industry. In the 50s and 60s, cars got faster and faster. And at some point, people realized if I can go 200 miles per hour and run into a wall and die immediately, that's bad. Okay, maybe I would still die with 200 miles per hour running into a wall. But if I have a crash with 50 miles per hour, I would still die. But the car would mostly be unaffected by that, by a crash at 50 miles per hour. With the cars, there are crash tests. You can search for them on YouTube. Crash tests from the 20s, where they have a car running into a wall, and the car basically looks like it took no damage. But the driver flew like a few meters out of the car because the driver takes all the energy. Yeah, so at some point people realized, okay, maybe we should have something like seat belts, maybe more seat belts. At some point, airbags. Nowadays, we even have airbags on the outside of our cars, if it's a modern car. ABS. So there's a lot of innovation going into safety, and maybe we should go through the same evolution, but with respect to security. Maybe we should think about, okay, it's great to be fast, but it's also great to not run into big trouble while doing that. So yeah, if you would think of a crash test, without seatbelts, things were quite terrible. Also, just a few years of difference, you see what a difference it made in the chances for drivers to survive. Also, something that we realized while working on Meltdown Spectre, but even more so working on Rowhammer, people are working a lot on defending against attacks. Also, when we published Meltdown and Spectre, there were already quite a few voices suggesting how to fix these issues. This is important. But what I faced, especially during my PhD, was often that people said, okay, why do you focus so much on attacks? You should focus more on defenses. After all, you want to make the secure a better place, right? And not just see it burn. And I was like, yeah, but if we only focus on the attacks that we already know and search for defenses against those attacks, do we even know the attacks we need to know? We overlooked Meltdown and Spectre for decades, right? So this sort of proved my opinion there. Maybe we don't know all the problems. I would see the set of all problems, it's a large set, and we know some small subset of the problems that are relevant to us. Do we at least know the most important problems, the most important subset? Or are we maybe hammering on a small subset of problems, working on solutions, small defenses against these problems, and forget about the bigger picture? So the question is what we learn from it. And maybe this is a unique chance to rethink processor design, grow up like other fields, the car industry, construction industry. They have standards how to do something. They have also independent institutions that check whether everything works as expected and has been done as expected. Maybe we need to improve on the communication between the different actors. Software developers make assumptions about how the hardware works, and hardware vendors make assumptions about what software developers will do. And those two don't match. Maybe we should work on the communication there. Maybe we should find good trade-offs between security and performance. And also, that's something I personally wanted to put here. Maybe we should dedicate more time into identifying problems and not solely in mitigating known problems. And with that, I'd like to close my talk. And if you have any questions, I'm open for discussion.
Thanks, that was a great talk. You mentioned the KPTI and Kaiser mitigations broke the page tables between userland to kernel, but the demonstration you showed was userland to userland, right? With the gedit shared library. Does that also?
That was not Meltdown. That was just a regular cache attack.
Oh, okay.
Yeah. And those still work out of the box. Yeah, there's nothing to. So I think there are no plans to mitigate those.
Okay, so we still have an entirely open kind of class.
Yeah, sure.
Yep, not solved. All right.
Yeah. If you have any idea, I think the important thing here is it's good to be aware of the problem and maybe have some brilliant mind come up with a clever defense against it, rather than keeping the problem secret and no one even thinks about the problem.
Yeah. Do you think that Meltdown and Spectre have been known to the Black Hat for the last 15 years?
I don't know. If it would, I would be so. Of course, if something like Meltdown could have been exploited potentially from JavaScript, and it would probably leave no traces because it would just be included in some JavaScript on some website and could read your kernel memory or physical memory, and I think there would be no trace. And after this surfaced, I would assume that anyone who would have had any evidence of their existence would have tried to get rid of the evidence. But I don't know. I think it would have surfaced earlier if it would have been known earlier, because it's difficult to keep some secret like that of that impact.
I have a question concerning the IPS, IDS systems which can detect the meltdown. Does it work really, or and how they detect it?
Yeah, so I've seen proposals that focus on the cache attack part, so detecting the flush and reload part. I have seen some proposals that look at the number of accesses to kernel memory that you perform. If you run Meltdown with TSX, you won't have any kernel exceptions, so not any segmentation faults that you need to catch in user space. So probably that part wouldn't work. And for the cache attacks, we have shown in the past that you can also do stealthy variants of cache attacks. Like instead of flush and reload, you would just measure the latency, not of the reload operation, but of the flush operation itself. And this already leaks whether it's in the cache or not. So you would do flush and flush instead. Yeah, whether they work or not, I didn't look at them in detail, but many of the proposals, I'm skeptical towards those. There was one.
Your point about the remote execution of Meltdown, if you think about it, you've got this high-end, high-performance extension from Intel, which allows you to have direct I/O from the network card into the level 2 cache of the processor direct. So, you know.
Yeah, that's, I'm aware of that.
We should do something about it. And the other one is regarding the branch prediction, you should also think about virtual machines with just-in-time compilers.
Yeah.
And binary translators.
Yeah.
Because those generate the branches at runtime,
yeah.
So you can't really protect with them.
But there it's, so there they are trying to automate this process into the code generation. And I'm not sure how well that works, but I think it's at least better than letting, so I think the worst thing is if the developer has to care about it, because every time the developer has to care about one thing more, it will go wrong in one or two places, right?
Yeah, hi. I tried actually to implement well, part of your work on ARM v7. And for the timings, RDTSC doesn't exist on ARM v7. So I used the threads, right? Built my own timer thread. And I ran into problems where when it ran, I didn't ever find the right threshold for Spectre, where I would see the difference between the cache miss and the cache hit. So I was wondering if you had an idea how to do this, or what I did wrong.
Yeah, on ARM v7, you don't have any flush instructions. So how do you throw things out of the cache there? Do you do that with cache eviction then?
No, I do it with some codes of assembly. It's also some prior research work, maybe not you, but other researchers, and there's a way to do that as well.
I think we have on GitHub a library that's called libflush.
Yeah, that's what I use, and but I changed a little bit the ARM assembly, which is not working for ARM v7. So it seems to be, my code seems to be working, but I don't get the difference between the thresholds.
Yeah. So that's the basic step for the cache attack, and it requires a lot of playing around with the eviction strategies that I would use there. I wouldn't use the flush instruction. It might not even. So I'm not sure what it does if the flush instruction is not unlocked. You would have to you can't even unlock it in ARM v7. So you would have to run the flush instruction in the kernel. And I'm also not sure whether that code is really working on all architectures. So probably, so I would go for eviction and there try different eviction strategies until you see some timing difference between the different cases. Yeah.
So those mitigations that are like on the microcode level, do they mitigate all of the overflows that you can have in like branch? I'm not sure if the branch target buffer can overflow, but there are apparently some overflows you can have in the return stack that the CPU keeps. Do you know if those are mitigated with that as well or not?
Yes, there is some buffer for a return address prediction on some processors. I'm not sure which models have that, but I would assume that most of the recent processors have that. I would have to look it up. But for some of them, yes, if the buffer for the return address prediction does not have any result, it would go to the branch target buffer. And yes, there's also some. I didn't look into at all the branch target buffer parts. I mostly focused on Meltdown, but there was some overflowing involved there that you need to do so that the misprediction works. Yeah. I'm not sure whether so that's nothing I would say you could get done with microcode patches. I think the focus there is rather that you don't predict in that case, or don't even have a value that you could predict in that case because it's tagged in a different way.
Hi. Do you know if anything affects GPUs?
As far as I know, so of course something like Meltdown might not be relevant for GPUs at all because they don't have any isolation on that level. If you have if you can do operations on the GPU, I would be surprised if there's not. I think there are multiple works that show that you can read any memory anyway. Then, as soon as you have access to the GPU, something like that. I think there is a work that will appear at IEEE SNP, Security and Privacy this year, but it's not public yet. And I think there were interesting attacks in that direction, but not related to Spectre or Meltdown. I'm not sure whether the GPU actually does speculate. I haven't looked into that.
No more questions? Okay, thank you, Daniel Gruss, for a great talk.